welcome to the Deep Dive. Today we're translating a really dense stack of engineering reports and architectural research into, well, essential knowledge. Our mission is to uncover the hidden lives of structural materials, looking at the science behind how buildings and everything inside them actually behave when they're exposed to fire.
Yeah, it's a field that I think most people don't really think about until they have to.
Exactly. You assume a building is either fireproof or it isn't. But the truth is much more complex. The materials really dictate everything: the fire spread, how the structure fails, your timeline for evacuation.
And even whether the building can be used again afterwards.
So we're giving you a shortcut to being fundamentally well-informed on all of this.
And it all boils down to three really critical criteria when you're looking at any building material in a fire.
Okay.
First is combustibility. Simple enough. How easily does it burn?
Right.
Second, and this is the big one, is its structural strength when it gets hot. Does it hold the building up? And finally, a factor that's often overlooked is the products of combustion.
What it gives off when it burns.
Exactly. The smoke, the toxic fumes. That last one often determines if a building is survivable, even if the frame is still standing.
So those three things: combustibility, strength, and toxicity. That's the lens for everything we're about to discuss.
It is.
Okay, so let's dive in with the big three structural materials. Steel, concrete, and wood. Let's start with steel. It's really the champion of modern architecture, right? That amazing strength-to-weight ratio lets us build these huge skyscrapers.
It's everywhere. Load-bearing columns, beams, you name it.
But here's where it gets really surprising. Unprotected steel fails, and it fails fast.
It fails incredibly fast. And it's a thermal failure, not a chemical one. Steel doesn't burn, but its mechanical properties just fall apart with heat.
So what's actually happening? The fire is on, say, the 10th floor. What's the steel beam doing?
Well, it's getting hot, and as it gets hot, it expands. We call it thermal expansion.
Yeah.
And it has to go somewhere.
And what does that do to the building?
It pushes. The beam tries to get longer and puts this incredible stress on the columns it's connected to. It can literally force the columns outward.
Wow.
And once those supports go, or the steel itself gets too soft, the floor slabs just lose their support. They collapse onto the floor below.
And that's the domino effect we always hear about in catastrophic collapses.
That's it, precisely. And what makes it so fast is steel's conductivity. It's a fantastic conductor of heat.
So it's spreading the problem.
It spreads the heat all through the frame, far from the actual fire, weakening the whole structure much faster than you'd think.
Do we have, like, hard numbers? What are the temperatures we're talking about?
We do. For standard mild steel, it loses about half its strength at 550 degrees Celsius. And for the high tensile steel, which is stronger and lighter,
I'm guessing it's worse.
it is, that loses half its strength at just 400 Celsius.
And a normal room fire gets way hotter than that.
Oh, easily. A fully developed fire can top 800 degrees.
So if the fire gets put out before the building collapses, is the steel okay once it cools down? Does it just, spring back?
Not really. It regains some strength, but its properties are almost certainly changed for good. The heating and cooling can cause microfractures, change the metal's internal structure. It can become brittle.
So you can't just trust it.
You can't. Which is why insulation, that passive fire protection, is so vital for steel. It's all about buying time before the steel hits those critical failure temperatures.
Okay, so that's the rapid drama of steel. Let's contrast that with concrete.
Yeah.
It just feels safer, heavier.
And in many ways, it is. What's fascinating about concrete is its resilience. Collapse is usually not sudden. It's a great insulator, so it slows heat transfer down dramatically.
It can often repair a concrete building after a fire.
You can. It's far more common to reinstate a fire-damaged concrete structure than a steel one.
So if it's not a sudden collapse, what is its primary failure mode in a fire?
The key mechanism is something called spalling.
Spalling.
Oh.
Okay, what is that?
Spalling is when the surface layers of the concrete or masonry literally break down and pop off in little chunks or pebble-like pieces.
What's causing that? Is it just the heat?
It's the pressure. See, concrete always has some trapped moisture inside it. When it gets superheated, that water turns to steam, expands, and it needs to escape.
And if it can't escape, it just blows the surface off.
It violently forces that outer layer off, and it can also be caused by the steel reinforcing bars inside expanding, or even the thermal shock from a firefighter's cold water jet hitting the hot surface.
So not all concrete is created equal in a fire.
Not at all. The type of aggregate, the stones inside the mix, matters a lot. Using lightweight aggregates can actually minimize spalling because it makes the concrete a bit more porous.
Letting the steam escape.
Exactly. And the other critical factor is the thickness of the concrete cover over the steel reinforcing rods. That cover is the protective shell for the steel inside.
Because if the fire gets through that cover and hits the steel rebar, you're right back to that 400 to 550-degree failure problem we had with the steel frame.
You are. And there's a neat little paradox there, too. Those steel rods can actually act as mini heat conductors, drawing heat deeper into the concrete and making spalling worse if the cover isn't thick enough.
All right, so steel fails suddenly, concrete erodes through spalling. That brings us to our third material, wood, which, wood just burns, right?
It does burn, but it's that predictability that is its saving grace, especially in modern engineered timber. It doesn't have that sudden, catastrophic strength loss.
So how does that work?
It all comes down to charring. As wood burns, it forms a black, insulating layer of char on its surface.
Okay.
And because wood is a terrible conductor of heat, that char layer acts like a natural fire protection system, slowing down how fast the heat gets to the unburnt wood in the core.
That's so counterintuitive. The part that's burning is actually protecting the part that isn't.
It is. The surface sacrifices itself to save the structural heart of the beam. So fire resistance comes down to a few things. First, thickness. A big, beefy timber column will last much longer than a thin one.
Because there's just more wood to burn through.
Yeah. Right. The charring rate is fairly constant. Second is density. Denser hardwoods offer better resistance. And what about the big laminated beams we see now? Glulam.
Yeah, how do those hold up?
They're fantastic for fire resistance. Engineers can calculate the charring rate precisely and design them with a specific sacrificial layer, ensuring the core stays strong for the required time.
And you mentioned joints.
Joints are always the weak point. Tight joints are crucial. They stop the fire from getting around the char layer and attacking the core directly.
Okay, moving beyond the big three structural materials, what about the things that, make up the walls and the windows? Masonry and glass.
For brickwork, it really depends on the type. Fired clay bricks usually perform better.
Why is that?
Well, they've already been through a furnace in manufacturing. They're pre-shrunk, They have less moisture, so they're more stable when heated again.
So it's the whole system, not just the brick.
Exactly. The thickness of the wall, whether it's load-bearing, and if it has plaster on it. A simple layer of plaster can add significant resistance time.
And what about stone? That feels like it should be indestructible.
Stone is actually highly unpredictable. Granite, for example, shatters pretty violently at around 575 degrees Celsius.
Wow.
Sandstone shrinks and cracks. Limestone can spall badly if it gets hit with water. It's just too variable.
Which brings us to glass. The obvious weak link in any fire compartment. It just breaks.
It's a terrible fire barrier. Your standard toughened glass, what some call armor plate, will fail at just 300 degrees Celsius, and double glazing is even worse.
Really? Why is that?
The trapped air heats unevenly, which creates enormous stress between the two panes, and they just shatter.
So once the glass goes, the fire gets a rush of fresh oxygen and can spread.
For a long time, your only option was that wired glass that holds the shards in place, but the real breakthrough is modern fire-resistant glazing.
With those intumescent interlayers you mentioned.
Exactly. They're clear layers inside the glass that when they get hot, they bubble up and swell into this opaque insulating foam.
That's incredible.
Yeah, the technology is amazing now. You can get glass that gives you 90 minutes of resistance.
And quickly, what about paint?
Most paint is flammable, full stop. It helps fire spread. But you can get intumescent paints.
The same idea as the glass.
The same principle. It swells up when heated and creates a protective char layer over the wood or steel underneath. It's a key part of the whole passive fire protection strategy.
This all covers the bones of the building. But what kills people in fires is often the contents, not the collapse. So even with a 60-minute rated structure, what's inside can change everything.
It is everything. The contents are the fuel. That's the fire load. Take something simple, like paper. Ignites around 250 Celsius, but shredded paper will flash over instantly, whereas a thick book is much slower to burn.
Right, surface area.
And plastics are probably the most dangerous element in any modern building.
It's because they're everywhere.
They're everywhere, and they pose multiple threats. You've got two main types. First, thermosetting plastics, things like epoxies. They decompose, create a lot of heat, but they don't melt. Then you have thermoplastics. Polyethylene, nylon. These are the ones that melt and flow when they get hot.
And that melting is a specific kind of danger, isn't it?
It is. The dripping molten plastic can spread the fire downwards to new fuel sources. But the most lethal danger from plastics is the smoke.
Right.
The sheer volume of thick, black, toxic smoke and carbon monoxide from burning plastics that's what makes a space unsurvivable so quickly. Cellular plastics, like foam insulation, are a huge hazard if they're not protected.
And what about fabrics, couches, curtains? They seem like the first things to go.
They're the accelerators. Natural fabrics like cotton tend to smolder first, but synthetic fabrics, which are mostly thermoplastics,
They melt.
they melt and shrink from a smolder, but as soon as they're hit by an open flame, they ignite and burn incredibly fast. Curtains can take a fire from a small source to a full room inferno in minutes.
Wow, this whole deep dive really shifts how you look at the materials around you.
Yeah.
So to summarize the core lessons here,
Yeah.
unprotected steel collapses fast.
Concrete resists well, but is vulnerable to spalling.
And wood burns, but in a very predictable way because of that protective char layer.
Exactly. And we deliberately engineer to improve all of this. We use lightweight aggregates, thicker wood, special coatings. It's all about buying time.
Pushing those failure temperatures further away.
But if there's one critical takeaway from all this, it's this. A structural beam might be rated for 60 minutes of fire, but the fire rating of the whole room, the whole building, is easily compromised by the decorative materials.
By the carpet and the couch.
Exactly. The fire isn't going to wait patiently for 60 minutes for the beam to fail if the room fills with lethal smoke in under 5.
That's the key insight. The difference between structural collapse time and the time until a room becomes unsurvivable.
There are two very different timelines.
So we focus so much on the beams and columns, but the speed and lethality of the fire might just be determined by the synthetic curtains or the plastic in the wall coverings.
That's the bottom line.
Which leaves you, our listener, with a really important question. When you're assessing a building's safety, are you considering the combustible contents just as much as the structural integrity of the frame? Something to mull over until our next deep dive.